In this next example, we have the cotangent of 7x. Now, we could try to substitute u equal to 7x, but the problem is we're going to end up with the cotangent of u, and we don't know what the antiderivative is of the cotangent function. So what we need to notice in this one, and they'll usually give us these identities for these problems, is that the cotangent is actually equal to cosine over sine. So my first step for this one is to do that substitution. I'm going to think about this as the cosine of 7x, so we'll keep the same angle inside, over the sine of 7x dx. And we're going to look for a substitution here. Now, one way to help see this a little bit better to decide what to do for our substitution is to actually break this up so that we're thinking 1 over sine of 7x times the cosine of 7x dx. Remember, we're looking for a function inside of another function. So if I look at that, notice that this sine of 7x is as if it's in the function of 1 over u. And so when we look at this, we think about which one's more complex. We could think of the sine being down in the denominator as being something that's going to be more complicated, and actually thinking of it as a function inside of another function. So I'm going to let my u be equal to sine of 7x, because again it's in that function 1 over u. Taking my derivative then, du will be equal to, the derivative of the sine would be cosine of 7x. Using the chain rule, we would multiply by 7 and keep our dx. We do not have a 7 grouped with this, so I'm going to move that out front, or over to the other side with du, which gives me cosine of 7x dx. Okay, so now we have a very clear substitution. This will get rid of our cosine here if I substitute 1 over 7 du. That means what I've substituted was that sine of 7x is now my u. I can take the antiderivative of that using natural log. Remember to use the absolute value of that natural log, plus c, and then we can plug in our original function. Our u was sine of 7x. In this next example, I notice sometimes they'll write this dx on the top here. We don't normally do that, but they do give us a substitution that they want us to do here. Right now what we have is a 1 over cosine squared of something. We can't just use that 2x because we don't know what the antiderivative would be for that 1 over cosine squared of 2x. But if we think of this 1 over cosine of 2x as being a secant, we could rewrite this as simply secant squared of 2x dx. Then if we're looking for a function inside, notice that this 2x is inside of secant squared. And so let's let our u be equal to that 2x. Using that, we would get du is equal to 2 dx. We have the dx, we don't have the 2, so let's use 1/2 of du being equal to dx. So using that for my substitution, we'll have 1/2 du. We'll keep our secant squared, except now we're using secant squared of u. We do know the antiderivative of secant squared, and that is tangent. And so we can substitute the 2x back in there, leaving us with 1/2 tangent of 2x plus c. For the next example, this is the substitution that we're given. Notice right now that's exactly what we have here. We have cotangent squared. They're suggesting we change that to a cosecant squared. We keep the same x we have here, 3x minus 1. Now this time, as we're looking for something to substitute for u, we have a couple choices. We could look at the fact that cosecant of something is being squared, so it could be all of that. Or we could also look at that 3x as being inside of the cosecant squared function. Now, the question to ask, do I know the antiderivative of cosecant squared? And we should know that the antiderivative of cosecant squared will give us a negative cotangent. So the substitution we'll use is that u is equal to 3x. Then we can get a du of 3 dx. We don't have a 3 here, so we'll move this 3 to the other side, have 1/3 du equal to dx, giving us a substitution of 1/3 and a du. And we'll keep everything else the same, except we'll plug in a u. We'll now take the antiderivative of this. Again, the antiderivative of cosecant squared was a negative cotangent. Antiderivative of 1 would be u, and then plus c. We can now substitute that 3x back in, so the cotangent of 3x minus 3x plus our constant, multiply the 1/3 back in, giving us negative 1/3, cotangent of 3x minus x plus c. In the next example, the substitution I suggest involves this. Notice that doesn't really match what we have here. The closest we could get is if I solve this for cosine squared, where we get 1 minus sine squared x. Now notice this is not cosine squared, but we're going to go with what they gave me. So let's write this instead as cosine squared x times cosine of x. That would give us cosine cubed, and it will also allow us to make this substitution here. And then let's see if we can work from that. And we had to do this because we don't know the antiderivative of this. So if I plug this in for cosine squared, then I'm going to look for a function inside of another function. Notice this sine squared is really, we could think of this as sine of x squared. And so I'm going to let my u be equal to sine of x because that sine of x is inside of another function. Now we may not be confident about that, but we can find out by checking. Let's take the derivative of this. That will give me cosine of x dx. And sure enough, that's exactly what we have after we've done the substitution. So substituting here, this would give me the du. This sine of x here will become u squared because it was sine squared of x. And we'll just keep the rest of that, the 1 minus something squared, keep our integral, and we can now take the integral of this. Take the antiderivative, 1 becomes u squared would become u cubed and 1/3 plus a constant. And now we'll substitute in the sine squared again, leaving us with sine of x minus 1/3 sine cubed of x plus c. If we're not sure, we could check it by taking the derivative of this.